Hi guys. Okay, so what I'm doing is number 62B, because I didn't catch this on the review when I didn't really look at the review, and I haven't gotten up to there in the key yet. But Frank brought it to my attention. So that means if you didn't learn this last year, then they're probably incorporating this alternate method. It's not a method, it's just an alternate format or notation for the Riemann sum. So let me just very briefly with Riemann sums. We know that we can't find the area under many of the curves we work with, right? And so initially what we learned to do was draw little rectangles underneath the curve. And we know that the more rectangles we have, the better the approximation we're going to get, okay? So here's a function from A to B, okay? And A is also noted as x sub naught, right? And the next increment would be x sub 1, x sub 2, x sub 3, all the way up to x sub n, okay? Which would be our B. And just a reminder that to find the width, so in other words, you know, if I want to compute the area of this first rectangle, I need the width, which is always the distance between x sub naught and x sub 1. And to find the width, we just do b minus a over the number of partitions, over n. N is the number of partitions. So, you know, I can compute, if I know the width, and I know the function's height, whether I'm doing a left or a right Riemann sum, what I know is that the area is the width times the height. So, for example, if I'm doing a left-hand Riemann sum, it'd be delta x times f of x sub naught, right? And I would get a1 here, this area. And then if I computed the next rectangle, again, if I'm working on a left-hand Riemann sum, I would have delta x times f of x sub 2 and delta x times f of x sub 3 for this height here, right? And the idea is we would add up all the areas and we'd get the sum, and that would be our approximation of the area under the curve, whether it's an overedge or an underedge or whatever. So the idea is that since I'm multiplying delta x by each height, I can factor out a delta x and just add up, you know, x sub naught plus f of x sub 1 plus blah 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 all the way until I'm done, left to right hand sum. Well, it's a sum. And another notation for a sum, and again, as the number of rectangles gets bigger underneath, right, the more rectangles we have under here, the closer and closer we get to the true area under the curve. So this is a limiting process. So the limit, as the number of rectangles increases, of the sum from some k equals to 0 to n, this could be a 1 to n, it could be a 5 to n, those indices can change, is equal to the height of the function. I'm used to working in x sub I, so anyway, I put an I there, but x sub k, that's the height of the function, times delta x, which is the width, okay? So what we have to do in a case like this, generally or simplistically, is we just need to rewrite this in this form. And it's really pretty easy because in general, we can say that the limit, so again, don't worry about the lower bound, from k equals, let's say, 1 to n, is our function. And this whole thing right here is going to represent the height, right, at a plus x, delta x times k times delta x. Okay, so this is the height of our rectangle and this is the width. So what you really need to do is know this little form here and think about what is the function, what is the lower and the upper bound, because you need them for your limits of integration, and delta x is just going to be dx, okay, in your integral. So this is what we're handed, this here, okay? Now if I compare it to this general formula, I know that my a is 1, and I know that my delta x is 5 over n, okay? So I know the lower bound of my limits of integration, it's 1. I know my function also is x cubed, right? This whole thing would be my x cubed. So, that being said, I know this so far, okay? Now, oftentimes you got to find the upper bound, all right? They'll always, generally for you guys, they're always going to give you the lower bound. You're going to have to find the upper bound. Well, you just use the fact that delta x equals to b minus a over n, and we know that our delta x in this problem is 5 over n. is equal to b, now minus our a was 1 over n, and if I multiply both sides by n, the n's cancel, so I'm left with 5 equals b minus 1, and solving for b we get 6. So your definite integral is the integral from 1 to 6 of x cubed dx. Now I believe this is a non-calculator section, which is insane for them to have an upper limit of 6, but whoever designed it probably wasn't thinking very hard. I mean, you can do it without a calculator, let's get real, but it's a pain. So anyway, the integration is nice and simple. It's x to the 4 over 4. We're going to evaluate from 1 to 6. Well, 6 to the 4th, I don't know that off the top of my head, so I'd have to multiply 6 to itself 4 times. Anyway, what it comes out to is 6 to the 4 over 4 minus 1 over 4. And 6 to the 4th is 1296 divided by 4 minus 1 over 4 gives us 1295 fourths, or 323.75. So chances are for this test, if you get one of these with this summation notation, you have to identify your a, which will always be this number, your function, so in this case it was x cubed, and your delta x is usually whatever is multiplied on the outside, okay, that way you can find your upper limit, and then you can rewrite your integral with what you know thus far, and chances are you're going to have to find that upper bound, and you're going to do it by using this. Okay, so I hope that helps. Sorry that I missed that, or maybe I saw it and figured you learned it last year, but again, if you didn't learn it last year, then it's probably because they might add it on to the AP exam this year. Just as a notation, nothing more. All right, have a good night.